At the end of section 1.3, we briefly discussed primality testing, or namely testing to see if a given number is prime. And we do that by using Theorem 10 in section 1.3 of the text. It states that if we have an integer n strictly greater than 1, and that n has no positive prime factors less than or equal to the square root of itself, then n is prime. And so this gives us a useful way to check by hand whether a number that's relatively small is prime. And so we'll see how to use this theorem with an example, but first let's prove it. So if I want to prove that n is prime towards a contradiction, suppose that n is not prime. Well, what does that say? It says that n is composite, and it also says that we can write n as the product of at least two positive prime factors. And we'll call those factors P1 and P2. So we have that n is equal to P1 times P2 as its prime factors, and then times some integer k. And k could be 1. K could also be the product of some primes. But for now, we're only focused on the fact that it has to be the product of at least two positive prime factors. Okay, so because we're assuming that n has no positive prime factors less than or equal to the square root of itself, we can say that P1 is strictly greater than the square root of n, and P2 is strictly greater than the square root of n by assumption. And so we get the following inequality. We get that n is equal to P1 times P2 times k, and that's going to be greater than or equal to, and I think I'll write this going down instead, greater than or equal to P1 times P2, because here we're not multiplying by k, and then that's going to be strictly greater than the square root of n times the square root of n from these above statements right here. But then the square root of n times the square root of n is equal to n. And so what is this saying? We're saying that n is strictly greater than itself. And that's a contradiction. So because we assumed that n was not prime and we arrived at a contradiction, that says that if we assume that n has no positive prime factors less than or equal to the square root of itself, then n has to be prime. And so now let's look at how we can use this theorem to prove whether or not a given number is prime. So we have the number 701. So first thing to note is that 701 is equal to the square root of 701 is equal to 26.476. And so the previous theorem tells us that if this number is prime, it has no positive prime factors less than or equal to 26.476. So let's list out the prime factors that are less than 26.476. So the primes less than 26 are given by the following. We have 2, 3, 5, 7, 11, 13, 17, 19, and 23. And so you can see here why checking this by hand is only suggested for relatively small numbers. If we had a very large prime, this would not be a practical way to check to see if it was prime. But this isn't too bad. So what we want to do is check to see if any of these primes divide 701. I've already done this. And so I can say that none of these divide 701. So 701 is prime. And so this is how we can use the theorem from the previous slide to check a number for primality.